Hi everyone, today's lecture will be in continuation with the last lecture. In today's session, we will be discussing about applications of derivatives. Okay, let's end this quickly so that we can start solving problems. So first is slope determination. So derivative is used to determine slope of a straight line. Determine slope of a straight line. For example, y is equal to x plus 3. If this is a line, then its slope is given by dy by dx. Differentiate this respect to x. So dx by dx1. Okay. If two lines are perpendicular, then product of their slopes is -1. For example, let m1 be the slope of first line and m2 be the slope of second line. Then product of their slope is -1. Yes. Derivatives are also used to find slope of tangent on any curve. For example, if y is equal to fx is a curve in xy plane, then dy by dx is equal to f of f dash x at x naught y naught is the slope of tangent at point x naught y naught, right? Second is increasing and decreasing function. So derivative of a function is used to check whether the function is decreasing or increasing, okay, on any intervals in given domain. So if we have a curve like this, right? So if this is the interval we are interested in, yes, so domain D1, domain D2. So if the function f is a strictly increasing function, then tangent to the curve y is equal to fx, okay, at every point in the domain D1 makes an acute angle with the positive direction of x-axis. Therefore, tan phi is greater than 0 right? So that means f dash x is greater than 0. Analogous to this, if we have a strictly decreasing function, so then the tangent to the curve y is equal to fx for all x in the given domain okay. So in the given domain makes an obtuse angle with the positive direction of x-axis. That means tan phi is less than 0, f dash x is less than 0 for all x in domain D2, for all x in domain D1, right? So meaning the function is increasing when its rate of change or derivative is positive and decreasing when its rate of change is negative. Clear? So let us check one function fx is equal to e raised to the power 2x, whether it is increasing or decreasing function. So differentiating with respect to x, we have f dash x is equal to 2 e raised to the power 2x, which is always positive or greater than 0 for all x. Yes, even if x is negative, say -1, so this will result in a positive value. Yes, so that means fx is strictly increasing function or monotonically increasing function. What if fx was equal to e power minus 2x? If fx is equal to e raised to the power minus 2x, differentiate with respect to x, we get minus e raised to the power minus 2 e raised to the power minus 2x. So since this is always positive e power minus 2x, but due to this negative sign, the overall this result is negative for all x. So that means fx is equal to e raised to the power minus 2x is a strictly decreasing function or monotonically decreasing function. So let me show you this with a plot. So this is fx is equal to e raised to the power 2x, and e power minus 2x, plot of fx is equal to e power minus 2x goes like this, right? So next topic is local maxima and minima. Local or relative maxima and minima. Local maxima would be the value of a function at a point in a particular interval for which the values of the function near that point are always less than the value at that point, or fx is said to be a local maximum or relative maximum at x is equal to a if there exist f a plus delta less than f of a. So if there exists a positive number of delta such that f of a plus delta is less than f of a for all values of delta. Okay, other than 0 in the interval minus delta to plus delta. Similarly, a function is said to be local or relative minimum at x is equal to a minimum at x is equal to a if there exists a positive number delta such that f of a plus delta is greater than f of a for all values of delta other than 0 in minus delta to plus delta in the interval. Okay. Maximum minimum values are also called extreme values, right? So let us understand this with the help of plot, a graph. Right? So okay, so local means we are interested in the neighborhood of A. Yes. So this means that if we consider a small interval around x is equal to a, then fa should be the minimum in that interval, and similarly maximum in that interval if this is a point, right? And whereas the absolute maxima would be the highest point of a point within the entire domain, right? So here in local maxima or minima, we are interested in a particular interval. Okay. So let us solve some problems. Let us find maxima or minima. Minimum values of fx is equal to 2x cube minus 9x square plus 12x minus 5 in closed interval 0 and 3. So since it is a polynomial function, so it is differentiable in its domain for all x. So differentiating with respect to x, we have 2 6x square minus 18x plus 12, right? So now find f dash x and equate to 0. So f dash x is equal to this, x squared minus 3x plus 2 is equal to 0. Then you can have x minus, that means either x minus 1 or x minus 2 is 0. So that means either x is equal to 1 or x is equal to 2. So we have two stationary point, 1 and 2 here. So let us check fx at 1. Sorry, we have to find f double dash x. Okay. Now differentiating again f dash x with respect to x, we have 12x minus 18. Okay. Now put the values of x in this. So if f double dash x is positive, then we have a minimum, and if f double dash x is negative, we have a maximum. So at x is equal to 1, this is at x is equal to 1, this is negative. So we have positive, we have maximum at x is equal to 1 and f double dash x is 24 minus 18 at x is equal to 2. Yes. So that means at x is equal to 2 we have a minimum value. Yes. So now let us put the value of x in the fx and then we can find the maximum and minimum value. So we had fx is equal to 2x cube minus 9x squared plus 12x minus 5. So now let us put the values of x. For maxima, let us put the value of 1, x is equal to 1. So 2 minus 9 plus 12 minus 5, that is equal to 0. Yes. And so this is a maximum, point of maxima. X is equal to 1 is point of maxima and the maximum value is 0. Again, at x is equal to 2, we have 2 cube minus 9, 2 square plus 12 to 2 minus 5, so which is equal to minus 1. So x is equal to 2 is a point of minima and minimum value is minus 1. Yes. So this is the working rule of to find out the maxima and minima of fx. So now next is this was the working rule for the function of a single independent variable. Now let us learn the working rule to find out the maxima and minima of function of two independent variables. Two independent variables let fxy be any function of two independent variables x and y, and now let us take partial derivatives p as del f by del x, q as del f by del y, then second order partial derivative r as del square f by del x square, s as del square f by del x del y, and t as del square f by del y square. Okay, now take p is equal to 0. So working rule, first take p is equal to 0 and q is equal to 0. Since p and q are function in x and y, so we have two equations in x and y. Solve the equation. Solve for x and y, and okay, so get the roots. Then second, so let's say you got x naught, y naught. x1 y1 okay, and so on. Now take a point, say x0 y0, find the values of, take a point, say x0 y0, find the values of r, s and t. Find okay, case 1, if if rt minus s square is greater than 0 and r greater than 0, then the function attains a minimum okay at this point, and minimum value is fx0 y0. Case 2, if rt minus s square is greater than 0 but r is less than 0, then function attains maximum at this point. Okay, so maximum value would be fx1 y1. Okay, okay, so now case 3, if rt minus s square is less than 0, then function has no extremum, then function has no extreme point, no extremum. Okay, and this is also called as a saddle point. Okay, so saddle point. The point at which you checked this satisfies is a saddle point. Okay, case 4, if rt minus s square is equal to 0, then this case is doubtful and further investigation is needed, right? Okay, so let us solve few problems, then you will get a more clear picture. Okay, let us take a function fxy x square plus y square plus 6x plus 12. So has, okay, you have to try this, a minimum at minus 3 comma 0, b maximum at minus 3 comma 0, c no extreme values, and d none. So now let us take partial derivative p with respect to x. So 2x plus 6. So assume y as a constant, and then q, while differentiating with respect to q, q with respect to y, df by dy. So assume x as a constant and you will have 2y. Okay, this is 0, this will be 0 and only 2y will be left. Now find the r. Okay, second order derivative of p, which is 2, and s. Differentiate p with respect to x. So sorry, s is del square f by del x del y. So either differentiate p with respect to y or differentiate q with respect to x. So which is 0. Yes. So now t, second order derivative of q, which is 2. So rt minus s square is equal to 4 minus 0, which is greater than 0, right? And r is also greater than 0. That means it is a minimum. Okay, so minimum at minus 3 comma 0. Okay, since r, s and t are independent on x and y, okay, so we did not check on this interval. Okay, so now let us take one more function, ax4 plus 6xy minus 2x square plus by square minus 2x plus 3. To find a and b, find a and b when x is equal to 2 and y is equal to 1 is minima and point of inflection or saddle point. Okay, so let us find p, del f by del x. 4ax cube plus 6y minus 4x minus 2. So at x. Now find q assuming x as constant, del f by del y. So which is 6x plus 2by. Now find out second order partial derivative. So del square f by del x square, which is 12ax square minus 4. Now s. So either you can take this way or del f by del x. Okay, so which is equal to 6. Then t is del square f by del y square, which is 2b. Okay, now at x is equal to 2 and y is equal to 1, put the values of x is equal to 2 and y is equal to 1 in r, s and t. Okay, so putting values of x is equal to 2, we have r as 48a minus 4 and s is 6 and t is 2b. So rt minus s square for minima, case of minima, we have rt minus s square is greater than 0 and r is greater than 0. So 48a minus 4 should be greater than 0. So a is greater than 1 by 12. Okay. And rt minus s square. So 48, this was from r greater than 0. So rt minus s square greater than 0 gives 48a minus 4 into 2b minus 6 square greater than 0. Solving, we will have 12a minus 1 b greater than 9 by 2. Okay. Since a is greater than 1 by 12, so we will have b is greater than 9 by 2 12a minus 1, right? So we have the condition a is greater than 1 by 12 and b is greater than, right? So next case is point of inflection. Okay. So point of inflection, we have rt minus s square less than 0. So 48a minus 4 2b minus 6 square less than 0. So which gives a is greater than 1 by 12 we had, and b is less than 9 by 2 12 a minus 1. Okay. So for case 1, this was case 1. Okay. So for if a is greater than 1 by 12, so then b should be less than 9 by 2 12a minus 1, and case 2, if a is less than 1 by 12, then b will be greater than 9 by 2 12a minus 1. Okay. So these are the two conditions of saddle point or point of inflection. Okay, first condition. And second condition. Next is homogeneous function. So an expression in which every term is of the same degree is called homogeneous function. So to test whether a function fxy is homogeneous, so put tx for x and ty for y in it. If you get f of Tx ty is equal to Tn fxy, then the function is homogeneous. Homogeneous of degree n. Right? Before proceeding to Euler's theorem, let us recall what partial derivative is. So, if we have a function of several independent variables and you have to find a derivative with respect to any one of them, keeping the others as constant, then it is said to be a partial derivative. So, and we use symbols like del by del x, del by del y, etc. to denote for partial derivative or partial differentiation. Okay. And second order partial derivative is del by del x so which can be denoted as del square u by del x square. So similarly del square u by del y square, del square u by del x del y, right? So if fxy and its partial derivative are continuous, so this is equal to del square u and del x del y. So the order of differentiation is immaterial. Okay. So Euler's theorem. If u is a homogeneous function of x and y of degree n, if u is homogeneous of degree n, then x del u by del x plus y del u by del y is equal to nu. Right? And this can be extended to a homogeneous function of any number of variables. Okay? Right? So now and this is applicable directly if u is an algebraic function. Okay, applicable directly if u is not algebraic, then and okay, first let us take this example. Let us say u is a naught xn plus a1 xn minus 1y plus a2 xn minus 2y square, okay, plus an yn, then x del u by del x plus y del u by del y is directly nu. Okay, but if u is not algebraic, then let, so this is case 1, and 2, if u is not algebraic, and let HU is algebraic and homogeneous of degree n in x and y, then x del u by del x plus y del u by del y is equal to n HU by h dash u. Let us see one example. If u is given as log x square plus y square, and then you have to find x du by del x plus y del u by del y. So let us assume, so let us take log on the left hand side. So e raised to the power u is x square plus y square. Now this is homogeneous in degree 2. Homogeneous. Now the answer will be, so x del u by del x plus y del u by del y is equal to 2 e power u by differentiation of this. So again this will be eu, which gets cancelled. So 2 will be the answer, right? Similarly, say you have u as x raised to the power 6 sine inverse x square plus y square by 2xy. Okay. See, if you put tx for x and ty for y, so this is t square x square plus y square and t square 2xy. T square gets cancelled, and here t6x6 sine inverse. So see, this function is homogeneous of degree 6. So x del u by del x plus y del u by del y is equal to 6u, right? Also, x square del square u by del x square plus 2xy del square u by del x del y plus y square del square u by del y square is equal to n into n minus 1 u. If u is a homogeneous function of x and y of degree n, then this is also true, right? So in this case, so this function is of order is homogeneous of degree 6, then this will be equal to 6 into 6 minus 1 u, that is 30u. Okay, let us see one more example. So u is equal to tan inverse x cube plus y cube by x minus y. So let us put tx for x and ty for y. Take t cube outside. Okay, and t x minus y. So if you take tan on left side, so now tan u is homogeneous of degree 2. So since this tan u is homogeneous of order degree 2, so formula was x del u by del x plus y del u by del y is equal to n hu by h dash u. Okay, so here hu is tan u, n is 2, so tan u, and differentiation of tan u is sec square u. So which is nothing but sine 2u. Okay, so this is the answer, right? And also x square del square u by del x square plus 2xy del square u by del x del y plus y square del square u by del y square is equal to gu g dash u minus 1, where gu is n hu by h dash u. Yes. Okay. So in this case, gu is two means sine 2u. Gu is sine 2u. And now put the value of gu here, then this also holds true. Okay. Okay, let me tell you what result you will get if you put sine 2u in the place of gu. So you will get g dash u minus one is equal to sine 4u minus sine 2u. Okay, check your answer. So next is total derivatives. Total derivative. So if u is equal to f of xy, okay, and x is equal to phi 1t and y is equal to phi 2t, then du by dt, then the total derivative of u with respect to t is denoted by del u by del x by del t plus del u by del y by del t. Okay. So in the same way, if you have u is equal to f of x, y, z, and x, y, z are all the functions of some variable t, then total derivative du by dt is equal to del u by del x by del t plus del u by del y by del t plus del u by del z by del t. Right? And this result can be extended to any number of variables. Fine. Okay. And if x and y are connected by an equation, of the form fxy is equal to 0, then dy by dx is equal to minus of del f by del x del f by del y. Okay. So next topic is series, Taylor series expansion. Okay. So if fx be a function defined such that fx is continuous in closed interval a plus h. Second, f n minus 1 is differentiable in a plus h. Okay. Then there exists at least one value theta belongs to 0, 1 such that f of a plus h is equal to f of a plus h f dash a plus h square by 2 factorial f double dash a plus h cube by 3 factorial f triple dash a plus up to h n by n factorial f. Okay, and the derivative of a, fa. Yes. So if we have to find the expansion of fx at point A, then let a plus h is equal to x. So which gives h is equal to x minus a. So fx is equal to f of a plus x minus a f dash a plus x minus a squared by 2 factorial f double dash a up to so on. Right? And Maclaurin series. So putting a is equal to 0, and h is equal to x in 1, okay, putting a is equal to 0 and h is equal to x in 1, we get Maclaurin series. So fx is equal to f of 0 plus x f dash 0 plus x square by 2 factorial f double dash 0 plus x raised to the power n by n factorial, okay, so which is known as Maclaurin theorem, right? So let us find the series expansion of sin x. Fx is equal to sin x so by using Maclaurin series, if fx is equal to sin x, put x is equal to 0 here, so f of 0 sin 0 is 0 plus x f dash 0 which is cos x and cos 0 is 1, so x, then plus x square by 2 factorial x square by 2 and f double dash 0 is so cos x, and again differentiate, then we will get minus sin x, and minus sin 0 is again 0, so this is 0, this term is 0 again you will get minus x cube by 3 factorial, okay, so you will get like this, x raised to the power 5 by 5 factorial. So this is an important series, and if you have to find out fx is equal to tan x, expansion of tan x, then again fx is 0, f0 is 0 plus x into f dash 0, so differentiation of tan x is sec square x, so that is 1 plus tan square x, and which is 1 plus again x square by 2 factorial and f double dash x, so one differentiating sec square x again with respect to x, so which will be 2 tan x sec square x, okay, which is again 2 tan x 1 plus tan square x, and so this is 0, so whole is 0, so into 0, so this way you can proceed, right? So next will be x cube by 3 factorial into 2 and so on, right? Here is the important expansion of the known series. So, and the expansion of these functions is required only up to first few terms, so you must remember this, okay. See, sin x is a odd function, so all the powers are odd, 1, 3, 5, 7, okay, and so are the coefficients, okay, and if the first term is positive and second term becomes negative, then it will alternate, so plus minus, okay. And similarly cos x is an even function, so powers are also even, so x bar 0, x bar 2, x bar 4, x bar 6 and 2, 4, 6, yes. So are the coefficients are also even, and plus minus it will alternate. So this way you can remember, right? Okay, let's wind up here. We will do problems on differential calculus in the next lecture. Then we will start integral calculus. Okay. And yes, I will share this notes on my Telegram channel. So you can find the link in the description below. Okay, then keep preparing. Thank you.